It's given by Professor Diogo Gomes, okay, who was formerly, until recently, chairman of mathematics. So, Diogo.
Thank you. Thank you very much. It's a great pleasure to be here. So today I'll be talking about some of the work that I've been doing on monotonicity methods for in-field games. And because I don't assume that everyone is familiar, although I see many faces here that were in previous workshops, I'll start with a very brief introduction about in-field games. And although this is a stochastic workshop, I'll do it just to be contrarian on the deterministic setting. So the situation is the following. You have agents. And for now, we start with a single agent. Maybe an agent watching this lecture. And what this agent can do is choose the velocity. And these agents control the velocity. And they have some cost or profit if you do the negative. For example, if you are in this lecture, maybe you are seeing some value in what I'm saying, as much as you can. But now I just changed the problem and I decided I'm going to charge you $100 by the end if you are still inside. And now you have an optimization problem, right? Because then you try to stay perhaps as close to the end as you can, but in the last minute you'll exit so that you don't pay my $100 charge. If you take the infimum over all your possible strategies, you get what's called the value function. And then there is something very classical in this optimal control, which is you build a Hamiltonian, which is the Legendre transform of the Lagrangian, the running cost. And it turns out that if you solve a Hamilton-Jacobi equation, which is a partial differential equation associated with this Hamiltonian, then you get the value function if you have smooth enough solutions, and you can obtain the corresponding feedback or your optimal trajectory. Now, the next thing is this. Well, now you have a deterministic vector field. You have a direction in where you want to move. And you ask, well, what would a crowd like this do? Or how would I describe a crowd like this by following a vector field and moving people around? And the answer is, well, a vector field induces a flow, which is just a map that tells you from where you were to where you are at time t, this phi t. And if you push forward, which you can think intuitively move people around according to this flow or according to the vector field, then what you obtain is that the distribution of agents will solve a transport equation. Now, the situation in mean-field games is that you have a very large number of agents, and each of them is solving a control problem, like the one attending my lecture and not paying the fee at the end. And this control depends on the other agents. For example, maybe there will be too much congestion at the end of the lecture, so we want to exit a little bit earlier. Maybe you'll miss some important points. So in fact, the situation is that the agents have a running cost that depends not only where you are, what you choose, the v, the velocity in this case, and the density or the distribution of the other agents. So what you actually have to do to find the value function is solve a Hamilton-Jacobi equation, which is the partial differential equation over there. Do you see it? Yeah, the partial equation over there. That depends on the distribution of agents. Now, if you couple these two equations, you get what's called the mean-field game. And the difficulty, or the thing that's good about this equation is that for a long time, we know pretty much everything about each of these two equations separately. So the theory of Hamilton-Jacobi equations in deterministic case, stochastic case, jumps, and so on is very well understood. The theory of transport equations, Fokker-Planck equations, jump diffusion kind of equation is also very well understood. The difficulty is that they are coupled, and they are coupled with initial conditions for M and terminal conditions for U. And this means that I know where you guys are now, so I know your initial distribution, and you know also the terminal cost at the end, $100 inside, $0 outside, right? And the evolution of M is forward in time, the evolution of U is backwards in time, but these things are coupled. So then you start wondering, well, what can I do, right? Because even if you want to design a numerical method, it's not obvious how to do it. Maybe you can run forward and backward, and run forward and backward and hope for some kind of fixed point. But even the convergence of this type of things is not completely obvious. And I've been involved in this kind of problems for a long time. And the answer for many years has been, well, you give me a mean field game, and then I'll get you some conditions, and then there is a proof of existence. Right? And then you give me another mean field game, maybe a parabolic version of this with some Laplacian, and I'll give you another type of conditions, another different proof, and another concept of solution, maybe, and then you have existence. And there are many results, and they really don't have a common thread. The type of techniques used to address each of these problems is mostly model specific. But it turns out that there is a uniqueness proof by Lasry and Lyons that actually depends on this equation can be seen as a monotone operator that allow us to construct general approach for solutions. And this is what I want to describe today. So how can we look at these problems? And well, I'll give you just a few things of what we can do, and then we can discuss more. So there are many variations, and for all of these variations, these monotonicity structures play really an important role. Essentially, these monotonicity structures are the only things that ensure uniqueness without substantially restrictive conditions. So let's start with monotone operators, something that was quite fancy maybe in the 60s and the 70s, and then we forgot all about it. And but they are really important for mean field games. And I mean, a monotone operator is the generalization, let's say, for functions from Hilbert spaces into Hilbert spaces of increasing functions. So my favorite Hilbert space is R, and in R, monotone operator is an increasing function. Increasing functions in R have nice properties. For example, they tend to have zeros. And when they don't have zeros, we also understand what's going on, right? I mean, maybe they don't cross the origin. They don't grow minus infinity. They don't grow to plus infinity in some pathological way. They also tend to have unique zeros, right? Because unless these functions are flat, the monotone function will cross typically once the origin, and you can easily understand what's going on. Another example of monotone operators is, moving forward or backward? Is this thing moving in which direction? Oh, I see. No, it's another thing. I thought this pointer was like mine. full screen. Okay, sorry. Because my pointer has a backward and forward in the same place. Okay, sorry about this. So gradients of convex functions are also monotone operators. And